Okay, good morning, class. Welcome back. It's 11 o'clock, so let's get on with what's on today's schedule. So before we start, as usual, do you have any questions for me? Do you have any comments, any issues, any difficulties? As I always say, remember to reach out if you don't understand anything. I'll try and make time and explain further, or do more examples with you. Yeah. Okay, so if there are no questions or comments, then let's continue from where we left off the last time. I'm sharing my screen now. If you can't see, do let me know. So on Friday, I think on Friday we were still working on implicit differentiation, right? Worked out everything from here. And then, yeah, so this was the last example we completed. And then the next thing is this example. So let's get on with the example 3. So for example 3, we have an implicit equation, right? You have x to the power 4 plus y to the power 4 equal to 16. And the question is asking us to find the second derivative, or y prime prime, right? So to obtain the second derivative, we know we have to go through the first derivative and then get to the second derivative. So let's try and first find y prime, or the first derivative, and then from there we can find the second derivative. So we are going to use implicit differentiation in this case, since this has an implicit, this is just an implicit equation, right? You have y to the power 4 here. It's not like y equal to an expression in terms of x. The y is mixed in there. So let's just do the implicit over there. So solution, let me say solution. So we just do d over dx of both sides. Right, and then you follow through with the derivatives, right? So for the first part, for the left-hand side, there's a derivative of a sum, and that's going to be the sum of the derivatives. So like so. Then the derivative of 16 is a constant, so that's 0, right? And then moving on, we have the derivative of s to the power 4, right? And that's what 4s cubed. And then the derivative of y to the power 4. Can you guys please help me on this? What do we get when we do d over ds of y to the power 4? Anybody? What do you think? What do we get when we do that?
Four y cubed.
Almost close. Yes. Yes, thank you. Yeah, so that's true. Thank you. So it's 4y cubed, but we are not done, right? Don't forget that for here, we're doing the chain rule because the y is some function of x. It's not just x, it's some function of x, right? So when you differentiate it by the chain rule, you have to differentiate the outer function, which is the power function. So that'll be 4y cubed. But please don't forget to do times the derivative of the inner function, which is dy over dx. You see, so yeah, that's exactly what I see in the chart. Yeah. So then that equal to 0. Now, when you get to this part, you just have to solve for dy over dx, right? So solve for dy over dx. So what I can do here is I can subtract the 4x cubed from both sides. So that'll give me 4y cubed dy over dx equal to negative 4s cubed. And then at this point, since I'm just solving for dy over dx, I can divide both sides by this 4y cubed, right? So this side divided by 4y cubed, and then this side divided by 4y cubed. So the 4's will cancel out, leaving me with dy over dx equal to what? Negative s cubed over y cubed, right? Now, the question asks for the second derivative, right? So to get the second derivative, you just have to differentiate the first derivative, right? So y prime prime, which is what the question is asking for, is just going to be what? The derivative of the first derivative. You see, it's just this one, the derivative of this. So let's just plug it in there. So we have d over dx of what? What we had for dy over dx is negative s cubed over y cubed, like so, right? So when you get to this part, then you just have to differentiate this, right? Now, going through the rules, looking at this directly, you can see that we are going to apply a specific rule. What rule do you think? What rule are we going to apply first? What do you see? Anybody? Perfect. Thank you, Regis. Yeah, it's a quotient rule, right? It's a quotient rule because it's a quotient. It's some function over another function. So by the quotient rule, what do we do? It's low, so y cube, d high. This time, let me attach the derivative to this. So that's the derivative of negative s cube minus high, so minus s cube, d low is d low is d over dx of what? Y cube, all about square of what is below. So that'll be y cube all square. Right? So moving on, we have y prime prime equal to, now for this first piece, right? The derivative of negative s cube is just negative what? 3s squared. And then this minus minus, so that's plus s cube. And then the derivative of y cube, that is just going to be what the chain rule, because the y is some function of x, so that'll just be differentiate the outer function, which is a power function. So that'll be 3y cube, plug in the inner function. Sorry, so 3y squared, and then times the derivative of the what? The inner function, dy over dx. And then all over. For this one, we have y cubed to the power 2, that will just be y to the power 6. Please, are you okay up to this point? Any questions? Okay, I'll need to move on to the next slide. So do let me know if you need more time here. Okay, then I'm moving on. So moving on to the next slide. So let me just repeat. So we have y prime prime, what you have up there. So this one is negative 3. No, let me just maybe simplify the pieces where I can. So we have y cubed and then negative, so that's negative 3s squared y cubed. So negative 3s squared y cubed. And then for the second piece, we have plus s cubed. And then for this part, we have times what? 3y squared. So let me bring the 3 in front. Okay, let me just do 3y squared. Okay, and then dy over dx is something we've already solved for. Remember that dy over dx is negative s cubed over y cubed. And in solving for the derivative, the second derivative, we don't need the first derivative in it. We need to what? Get it in terms of x's or x and y's in this case, right? So we have to plug this back in. So dy over dx is negative s cubed over y cubed. So we have to bring that there. So that would be negative s cubed over y cubed, right? I think that was the only piece, yeah, missing. So we have it here. And then all about y to the power 6, right? And then at this point, you can choose to simplify. Now I have it in x's and y's. By implicit, it will accept it, but you can also choose to simplify if you want to, right? So at this point, let me see. I can, since I have y cube here, perhaps let me just do this. So I have this is equal to, I'll multiply. So this cube, this is squared. So okay, I'll multiply the top and bottom by y. So I get negative 3s squared y cube plus so 3s cube y cube, sorry, y squared, yeah, and then times what? Negative s cube over y cube, like so, right? All over y to the power 6. And then in doing this, I can just distribute the y through, so I get negative y s squared y to the power 4. And then this part will be plus 3s squared s cube, and then this will be y cube, y squared times y, that's y cube, and then it will cancel out. That's the main reason why I did that multiplication. So they will cancel out. That will just give me a negative s cube on top, right? Yeah, and then all over y to the power 6. No, times y, right? Let me bring the y in. Yeah, there's another y here. So then simplifying further, you can have negative 3s squared y to the power 4 minus 3x to the power 6 all over y to the power 7. As I said, on an exam, please don't spend too much time to simplify. Immediately you get your answer, you can just put it in. WebAssign will accept it, I'll also accept it. So that's it. You can even simplify more if you want, but yeah, I think this will do for now. Yeah. Please, any questions on this? So that's how you get a second derivative. So the new idea is that when you're doing the second derivative, using implicit, you get the second, you get the first derivative inside it, you see, like this, and then you have to just plug it back in from the previous step, like when you're getting the first derivative, and just plug it back in, and then everything will simplify. That's all. Please, any questions on obtaining the second derivatives? Okay. Anybody needs time here? Okay, then let's move on. So now we're going to learn another group of derivative rules, right? So this is about inverse trigonometric functions. So for inverse trigonometric functions, let's start with the sine. For that one, let's go and derive it from the whiteboard, and then I'll walk you through this on the PowerPoint. So suppose we have y equal to sine inverse of x, right? Now let's try and find this, right? So that's what we are trying to find. Okay. Now, if y equal to sine inverse of what? Of x, then you know that sine of y will be equal to x, right? If y equal to sine inverse of x, then sine of y will be equal to x. Okay. Now that we know that sine of y equal to x, under this condition, if you have y equal to sine inverse of x, then the range of values for y is between negative pi on 2 and pi on 2. Right? Okay. So now that you have this, you have sine of y equal to x. This is an implicit equation. So you employ implicit differentiation to try and obtain the derivative. Let's try and find y prime. Right? That's what you're trying to find. You're trying to find the sine inverse over dx, which is the same as finding the y prime when the y equal to sine inverse of x. So we just do d over dx of what? Of both sides. So we have d over ds of sine of y equal to d over ds of x. And then for d over dx of sine of y, don't forget that the y is a function of x. So on this left-hand side, we will have to employ the what? This is going to be what? The chain rule, because sine is an outer function, and then the y, which is some function of x, is an inner function. So by the chain rule, what do? You differentiate the outer function, right? The derivative of sine is what? Cosine. Plug in the inner function. So I'll plug in y times the derivative of the inner function. So that'll be dy over dx. And then that will be equal to the derivative of x with respect to x, that's just 1. Right? So that will leave us with cosine of y dy over dx equal to 1. But the question is asking for dy over dx, right? It's asking for dy over dx. So we will just solve for dy over dx like how we do it the normal implicit approach, the normal implicit way. We know that dy over dx is equal to what? 1 over cosine of y. Right? Okay. Now the question is, do we end here? And then the answer is no, right? When we're doing implicit differentiation, the main idea why we left the y in the solution, like I mean in the solution in the sense that for implicit, we could have something like x over y, the derivative of y equal to what? X over y. We could have something like that. The y was mixed in there with the x. But for this case, we can't leave it in terms of y. Why? Because we have an explicit solution for y. At the beginning, we have an explicit solution. We have y equal to sine inverse of x. So since we have an explicit solution for y, we need to also get an explicit solution for what? For the derivative. So that's how that works. Right? For implicit, we don't have any other option. We don't have an explicit solution for y. That's why we leave the answer in terms of, we leave the answer of the derivative in terms of x's and y's. But if we have an explicit solution, you have to leave your answer in an explicit way, like only in terms of x. So let's do that here. So let's try and find cosine of y, right, in terms of x. Now, to do this, just note that from Math 127, pre-calculus 2, you know that sine squared of y plus cosine squared of y equal to 1, right? Now I'm trying to solve for what? Cosine of y. So I have cosine squared of y equal to 1 minus sine squared of y, right? Now, within this range of values for y, cosine is always positive, right? So that means if I'm solving for cosine of y, then cosine of y is square root of what? 1 minus sine squared of y. Now, I'm not doing plus or minus here because, as I said, within this range of y values, the cosine is always positive. Between negative pi on 2 and pi on 2, the cosine of y is always positive. So that's why it's not a negative square root. It's rather a positive square root, only the positive part. But then what is sine squared of y? Well, I know sine y equal to x. So that means that cosine of y will be equal to what? 1 minus s squared, right? Sine y equal to x. So I can just substitute this here and then I get this. So now I've been able to get what? Cosine of y in terms of x, right? So with this, I can just put it back in the derivative and then get what? My derivative. So that'll be 1 over square root of 1 minus s squared. So that's why the derivative of sine inverse of x dx is equal to what? 1 over square root of 1 minus s squared. So if you don't understand any of the proofs that we did, or you don't grasp everything, at least this is something you have to take away. This is the thing you have to know. The derivative of sine inverse of x with respect to x is equal to what? 1 over square root of what? 1 minus s squared. Okay. Please, any questions on this? Any part you don't understand? Okay. Anybody needs time here? But the proofs is still on the PowerPoint, so you have notes already on that. Okay, I'm moving on to the next slide if you don't need time. Okay. So now let's look at another one, another trig, inverse trig function. So let's check out tan inverse of x. What's the derivative of tan inverse of x, right? What's this? Okay, so for this one, you proceed in a similar manner, right? Since we have y equal to tan inverse of x, that means that tan of y equal to x. And then we still employ the implicit, right? So we do d over ds of tan of y, so of both sides. So that's d over ds of x. And then the derivative of tan of y, that one we have to employ the what? The chain rule, where tan is our outer function and y is somewhat inner function. So by the chain rule, differentiate the tan. What's the derivative of tan? That one is secant squared, right? Plug in the inner function. So that'll be secant squared of y. And then times the derivative of what? Of the inner function, equal to 1. So if you're solving for dy over dx, you get 1 over secant squared of secant squared of y. But as we saw for the previous case, we have an explicit solution for y. So you have to leave your answer in x. So let's try and get secant squared of y in terms of x. So for that one, you fall on this property, right? From Math 127, you recall that secant squared of y should be equal to 1 plus tan squared of y, right? From Math 127, some of the trig identities. Okay, so based on that, and then the fact that we know that tan of y equal to x, that means that in our case, we know that secant squared of x, secant squared of y equal to 1 plus what? S squared, right? Because tan of y equal to x, right? So 1 plus s squared. Now, with that said, we can just get our dy over dx, which is equal to 1 over 1 plus s squared, right? So the takeaway is the derivative of tan inverse of x dy, dx is equal to d tan inverse of x over dx is equal to what? 1 over 1 plus s squared. So that's the takeaway, right? Now there are other four, there are other 4 trig identities, but at least I've shown you the proofs for the 2 of them. The other 4 are going to follow one of these patterns. Either is following the proofs we did for the tan inverse or the proof that we did for the sine inverse. So it's going to follow either one. So we are not going to prove them, right? Those ones will be direct, but you can work it out if you want to. But please, do you have any questions on this before I move on? Any issues, any comments, any part you don't understand? Okay. Okay, then I'm going to the PowerPoint. Okay, so this is just notes, right? It's just going over what I just said. But then the takeaway is that sine inverse, the derivative of a d over ds of sine inverse of x is 1 over square root of 1 minus s squared. And then the derivative of tan inverse of x is what? 1 over 1 plus s squared. So with those two obtained, let's try and get these two. Let's try and get these derivatives, like for the a and b. So let's do that on the whiteboard, since the solution is already on the PowerPoint. So this is example 4. Example 4. Okay, so A, we have y equal to 1 over sine inverse of x. And then the question is asking for the derivative, right? Let me let me write a b here so that I don't have to go and check the arctan square root of x. Okay, so these are the two questions, right? So let's check out the solution. So for the first part, right? So for A, if you're asked for dy over dx, then you know that this is just going to be attach the differentiation operator to this. So you have 1 over sine inverse of x, right? Now, when you get to this point, you can decide to employ the quotient rule, right? But the quotient rule will be, I mean, it's correct if you employ the quotient rule, that works, but I want to use a different route, right? I'm going to rewrite this as sine inverse of x all to the power -1, so that I employ the chain rule, right? I can write it like this. Okay, so if I'm able to write it like this, then I can see this to be what? A composite function, where this is my inner function, and then my outer function is some power function, right? So that means that my dy over dx in this case will be equal to, so how do you differentiate the outer function, which is a power function? Well, the power function, you bring the power down, and then you subtract 1 from the power, but then plug in the inner function. So that'll be this, plug in the inner, subtract 1 from the power, times the derivative of what? No, this will make it look like x. Let me do times like so. Times the derivative of what? The inner function, which happens to be the derivative of sine inverse of x, right? So that means dy over dx will be equal to, we have -1, and then we have sine inverse of x, and then -2. Now, for the derivative of sine inverse of x, do we have a standard derivative for that? Yes, we just saw that, right? The derivative of sine inverse of x is 1 over square root of 1 minus s squared. And then that's it. We are done, right? As I said, you can simplify further if you want, but simplification is not the focus here, right? So you can just type this in and you're done. Okay. Any questions? Any part you don't understand? Anybody needs time here? Okay. Then let's go to B. So for B, we have f of x, right? So we are asked for f prime. Let me see. Yeah, so f prime is just attach the differentiation operator. So you have d over dx and then arctan. Now, arctan is the same as tan inverse. So I think that one will suit just fine. Let me write it as tan inverse. So that's tan inverse of square root of x. Okay. Now, for this piece, you ask yourself, do you have a direct derivative of tan inverse of square root of x? No, I don't have it. I have it for tan inverse of x, right? But then, oh, wait, did I miss something? I think it's x first. Yeah, there's x. I missed the x here. That was a close shave. Okay, so let me erase this. Yeah, so it's x tan inverse of that. Yeah. So the question is, do you have a direct derivative for this? No, we don't. Is this a composition directly? No, it's not a composition. This part is a composition in itself, but together with the x, it's not a composition. So first and foremost, this is a product of two functions, right? It's a product of x and tan inverse. So you have to first employ the product rule. So the product rule says, leave one alone, multiply by the derivative of the second function, plus, I think this one, I'll need all the space I can get. It's going to be long. And then plus, leave the second function alone, multiply by the derivative of the first. So that's d over dx of x, right? So for the first piece, let's look at where this derivative is. And the question is, do you have a direct derivative for this? No, we don't have a direct derivative for tan inverse of square root of x, but I can see this to be like a square root of x as an inner function. And then the tan inverse is my outer function. Do you see? So if I have that to be the case, then I can employ the chain rule. So by the chain rule, it says differentiate the outer function. But the derivative of tan inverse of x is 1 over s squared. So that'll be 1 over, sorry, it's not 1 over s squared, it's 1 over 1 plus s squared. So that'll be 1 over 1 plus what? X. But we don't put the x there, we have to plug in the inner function, right? So plugging in the inner function, I have to put the square root of x there and then square this instead. These are okay. The derivative of tan inverse of x is 1 over 1 plus s squared. But then I have to plug in the inner function. Wherever I see x, put in the inner function. So that means that'll be 1 over 1 plus square root of x all squared. And then don't forget to multiply that by what? The derivative of what? The inner function. Now, the second term is just straightforward because the derivative of x is just 1. So that'll just leave us with tan inverse of square root of x. And then let's continue. So for this side, I can write this together as x over 1 plus x. And then for this side, the question is, do you have a direct derivative for square root of x? Well, for that one, we can employ the power rule because square root of x is the same as what? Square root of x is the same as what? S to the power 1/2. So we just employ the power rule there. So that'll be what? Bring the power down, multiply by, and subtract 1 from the power. Then plus what? Tan inverse of square root of x. So putting everything together, you can get it to be x over, I mean, as I said, you can always simplify as best as you can, but simplification is not the goal in this section, right? So you can write this as this, and then 1 plus x. And then, yeah, I think that's all. Yeah, that's all for this. You can even simplify the radical, but simplification is not, there are so many ways. The web assignment will accept it at this level, to accept this answer, this level. You are right. You can type in the -1/2 minus 1, like the half minus 1 and everything. It will give you, it will say you are right. Yeah, so you don't have to focus too much on simplifying. As long as you take the derivative, you are fine. Okay. Please, any questions on this? Is there any part of the derivatives that you don't understand that you want me to go over? Okay. Anybody needs time here? Okay, then let's just go back. Let's switch to the PowerPoint, which will have the solution on it. Okay, so for these two, for the first one, we did this, just similar to what we did. It simplified a bit. And then for the second one too, first product rule, and then you get this, yeah. Now it rationalized the denominator. That's how come we have square root of x here. For our answer, we had x here and then square root of x down here, but it's still the same thing. Okay. So now there's just a list of the whole thing, right? The list of the inverse trig functions. The derivative of sine inverse of x is equal to 1 over square root of 1 minus s squared. The derivative of cosine inverse of x. Well, the trick here is just memorize these three. You just need sine inverse, you need tan inverse, and you need secant inverse. The rest are just the negatives of them. The cos are just the negatives of their corresponding trig related quantities. Like what I mean by that is sine inverse, the derivative of sine inverse of x is 1 over square root of 1 minus s squared. The derivative of cosine inverse of x is going to be the negative of what? The sine inverse. So that's -1 over square root of 1 minus s squared. You see, and so on and so forth. Yeah, so you can employ that trick here and then use it to memorize. But you need to know all of these rules. Yeah. Please, any questions on the rules? Okay. Anybody needs time here? Okay. Okay, so now with that said, let's look at this derivative. So now we have everything, right? We have all the derivatives together. So let's try and work this out. So for this one, we have to differentiate secant inverse of x squared. So I go, okay, so j prime is what we are asked for. Just attach the differentiation operator to secant inverse of s squared. And then at this point, I ask myself, do I have a direct derivative for secant inverse of x squared? No, I don't. I have, the closest I have is for secant inverse of x. This is not secant inverse of x, it's secant inverse of x squared. So that means there's some inner function, and then that is an outer function, right? So with this one, if I'm able to identify this to be a composite function, then I have to think about the chain rule. So by the chain rule, differentiate the outer function. What's the derivative for secant inverse of x? Well, the derivative for secant inverse of x is what? It's 1 over x square root of s squared minus 1. This one. You see, 1 over x square root of s squared minus 1. So you do 1 over, but you don't write x. You have to plug in the inner function. So wherever you see x here, you have to put in what? The inner function. So it's going to be 1 over s squared, square root of what? S squared. So that'll be s squared minus 1. Right? But please don't forget to multiply by the derivative of the inner function. That's the derivative of s squared. So wrapping everything up, you have 1 over s squared and then square root of s to the power 4 minus 1. And then times what? The derivative of s squared is just 2x. Right? So that's it. Yeah, you can leave your answer here and then you are right. Okay, please, any questions on these examples? Are you okay? Okay. Anybody needs time copying this? Okay, then let's move on to that. That's the end. I think that's the last, yeah. That's the end of 3.5. Save. Okay, so let's move on to 3.6. Okay, so I'm sharing the PowerPoint for 3.6 now. So derivatives of logarithmic functions. So for this one, let's look at some of the logarithmic functions we know, right? So for a logarithmic function, we're looking at y equal to log base b of x, right? So log base b of x. So one common function is the natural logarithmic function, which is when the b, which is the base here, is e, right? Log base e is the same as ln. So that's ln of x, right? So how do we get the derivatives? So for this one, let's go to the whiteboard and then try and figure it out. So this 3.6. Okay, and then this logarithmic function. So we are looking at y equal to log base b of x. What is the derivative, right? What is dy over dx? What is it? Okay, so now to try and get the dy over dx, we employ a similar tactic like the one we employed in the inverse trig functions. We know that whenever you have a logarithmic statement, you can convert it into an equivalent exponential statement. So if you have y equal to log base b of x, then it's the same as b to the y equal to what? Equal to what? X. The base here to the answer equal to what? What is in front of the log here. So now when you get this, since you're trying to find dy over dx, you employ implicit differentiation. So you do d over dx, b to the y equal to d over dx of x. And then at this point, you differentiate this, right? The base is a constant, right? So the question is, do you know how to differentiate what's the derivative of b to the x? Well, the derivative of b to the x is b to the x ln of b, right? So if you have the derivative of b to the y, and then y is some function of x, then the same as a composite function, right? So the b is your outer, the b to the x is your outer, and then the y is your inner function, right? So by the chain rule, you differentiate the outer function. The derivative of b to the x is what? B to the x ln of b. But we plug in the inner function. So that means that would be what? B to the y ln of b. And then you multiply by what? The derivative of the inner function, which would just be dy over dx. And then this is equal to what? What's dx over dx? That's just 1. Right? So dy over dx will just be equal to what? 1 over b to the y ln of b. But similar to what we had for the inverse trig functions, we had an explicit solution for y. Whenever you have an explicit solution for y, you should leave your derivatives in terms of what? In terms of that independent variable. So you have to leave everything in terms of x, not y. It's not like the implicit case where we didn't have a solution for y. We didn't have a solution for y. So when we got our answer, we left it there. This time you have an explicit solution for y here. So you have to put it in here. Now, note that b to the y is just x from this line, right? B to the y is just x from here, you see. So that means that we have dy over dx equal to what? 1 over what? X ln of b. So the takeaway is when you're doing d over dx of log base b of x, is just going to be 1 over x ln of b. And that's the takeaway. Okay. Please, any questions on the proof? Any part you don't understand? So that's also another rule. Okay. So now, if you have it for this, then what is the derivative of ln of x? Well, ln of x is the same as log base e. So using this thing that we got here, this expression that we got here, that means that this case it should be the same as 1 over x ln of what? The b. The b is e in this case. So that's ln of e. But what is ln of e? ln of e is 1. So that means the derivative of x ln of x. That means the derivative of so d over ds of ln of x is just 1 over x. And there's also another takeaway. Right, so 2, right? Now this is a more general one, but this is another one, another takeaway. right? So the derivative of ln of x is just 1 over x. Please, are you okay with this? Any questions on this? Anybody needs time? Yeah. Okay, then let's move on. So now the other third thing, the third rule you are going to obtain is something that you may not need, but it cuts out your work a little, right? So let's try and find this. What's the derivative of ln of some function? Well, this is not different from a composite function where your outer function is the ln and your inner function is what? Is g of x. Is the inner, right? So you can think of the chain rule. So by the chain rule, differentiate the outer function. What is the derivative of ln of x? We just learned that the derivative of ln of x is just 1 over x. But don't forget, we plug in the inner function. So wherever we see x, we have to put in g of x. So that means 1 over x. No, we have to do 1 over what? G of x times the derivative of the inner function. Right? So you can employ the chain rule here, no problems. Whenever your outer function is ln, no harm, right? No issues. However, it's easier to think of it in this way. Whenever you have a composite function where your outer function is ln and your inner function is g of x, then it's just going to be differentiate the function, divide by the function itself, right? Because 1 over g of x times g prime is just g prime of x over g of x. So there's also another takeaway. Please, are you okay with this? So whenever you are dealing with the derivative of a composite function and your outer function is ln, just differentiate whatever is inside, divide by the function itself. It's an easier way to think about it, but you can still use the chain rule and it still works. No problems. Okay, please, any questions here? So those are the 3 rules you have to know for logarithmic differentiation. Okay, I'm going to switch to a PowerPoint, yeah. If you need time here, do let me know so that we do more examples there. Okay, I'm here. So these are the ones we obtained. The proofs are not shown here, but I've just shown you how we obtained them, right? So the derivative of log base b of x is just 1 over x ln of b. The derivative of 1 over ln of s is just 1 over x. Then the derivative of, this one is Leibniz notation, so you can ignore this. But the derivative of ln of g of x is just differentiate the inner function, divide by itself, right? Okay. Oh, the proofs are provided here. Please refer to whiteboard. I provided a slide for this whiteboard for proofs. Okay, so now let's look at the first example. So differentiate this. Maybe, can anyone please help me with this? Please try your hands here. What do you think? What is y prime? Can anyone please help me here? What is this? Anybody? What do you think? Okay. I have 1 over, yeah. So feel free, try your hands. Yeah. Okay, that's good. Thank you, Megan. Yeah. So 1 over 3x squared. A different answer or a second that? Feel free to speak your mind. If you get it wrong, that's fine. Sometimes when you make a mistake, it helps you to remember better because you remember, oh, this one I got it wrong in class when I made a contribution and we answered it to be this way. So I'm not going to forget it on this exam, something like that. Yeah. So thank you for your response. But let's try and think about this together. Now, recall this one, there are 2 ways to think about it, right? You can use the rule. Okay, so I have a different answer, a different setup. Thank you. So you can use the rule that the derivative of ln of g of x is just what? The rule that we just obtained. It just differentiate the function, divide by itself. Or you can think of what? The chain rule. If you think of this as a chain rule, then this is your outer, and that's your inner function. So the derivative of the outer, which is ln of x, is just 1 over the function, right? But as I said, the rule that we obtain here, this recall thing that I wrote, it will be easier to think of this in this sense. Whenever your outer function is ln, just differentiate the function inside. So what's the derivative of s cubed plus 1? That's just 3s squared. Divide by the function itself, s cubed plus 1. We are done. That's all. You see, that's easier to think about than the chain rule, but the chain rule still works. all the same, right? Yeah, so that's our answer. We're done. Okay. Please, anybody needs time here? Okay. So what about this? Can anyone please help us with this? Does this one has a solution on it? Oh yeah, it does. It does have the solution. Okay, yeah. But please, what about this? Anyone? What do you think? The outer function is ln. So what do you say? Cosine over sine. Thank you. Okay, different answer, a different a seconder. Yes, yes. Okay, so more like a seconder. Thank you. Yeah, I have a seconder today, so let's continue. So for this one, we see that, oh, the outer function is ln, and then the inner function is sine of x. You can do the chain rule, as I said, no problems, right? But the easier way to think about it is whenever the outer function is ln, just differentiate the inner function, divide by itself. So the derivative of sine is what? Cosine. Divide by the function itself, sine of x. I'm done. That's all. Right? So that's what this is showing you, right? Now, I think this one used the chain rule, right? It acknowledges as outer, inner. So the derivative of the ln of s is 1 over x, but we plug in the inner function. So that's 1 over sine of x times the derivative of what? Sine of x. So it's good to see the two rules at play here, right? So you get this, which is the same as this. And then cosine of x over sine of x is cotangent of x. But wherever sine was set cosine of x over sine of x, it also has set cotangent of x, either one. Okay. Please, are you okay here? Any questions? Okay. So then let's differentiate this. For this, let's do this together. So solution. So I'm trying to find f prime of x. So that just be d over dx of what? Now ln of s is ln of x to the power half. Square root of ln of s is ln of s to the power half. So for this one, I can employ, it doesn't look like any of the rules you've seen. It's not like ln of j of x or ln of s or log b is b of x. It's none of those, right? But for this one, you can see that this is what? A composite function where your inner function is ln of x and then your outer function is some power function, right? So by the chain rule, you differentiate the outer function. So that'll just be bring the power down, plug in the inner function, and then subtract 1 from the power, right? That's the power rule. Then please don't forget to multiply by the derivative of the what? The inner function, right? And then the next thing we do is we focus on the derivative of ln of x. So the derivative of ln of x is just 1 over x, right? So that'll give us half ln of x to the negative 1/2 times what? 1 over x. And that's our final answer. Okay. Please, are you okay with this? Any questions? Any part you don't understand? Anybody needs time here? Okay. Now let's look at another example. So we are looking for f prime of x. So that just be d over dx of what? Log base 10. And then 2 plus sine of x. So this is not ln of something. This log base 10, right? So it's different. So for this one, what do? We have to employ the chain rule, right? So this is our inner function. And then our outer function is log of base 10, right? But note that we just obtained this derivative. The derivative of, oh no. So d over dx of what? Log base b of x is equal to what? 1 over x ln of b, right? So with this in mind, we are going to do what? The derivative of the outer function will be what? 1 over x, but we don't write the x. We have to plug in the inner function. So that will be 1 over 2 plus sine of x, right? And then ln of what? 10 times the derivative of what? The inner function. So that'll be 2 plus sine of x. Please, are you okay with this? Any questions on the approach? Now, after getting this step done, you just have to focus within this one. So where the differentiation operator is attached, right? So the derivative of 2 is what? Is 0. And the derivative of sine is cosine. So that means you get what? 1 over that 2 plus sine of x ln of 10 times the derivative of sine, so cosine of x. And that's your answer. That's your f prime. Okay. Please, any questions here? Okay. Anybody needs time here? Okay. And let's move on. Now, what about this example? So we have d over dx of what? ln of s plus 1 over square root of x minus 2. Well, for this one, if you employ, you see the outer function is ln and the inner function is something. So you can differentiate the inner function, divide by itself. But as you can see, we have a quotient rule inside there. It's going to make it complicated. You can still do that, it still works. But I have a different way that I can do this, right? Which will be easier. Properties of ln. Now remember some of the properties of ln, right? When you have ln of x times y, then it's just ln of what? X plus ln of y. Right, so remember this. When you have ln of x over y, then it's just ln of x minus ln of y. And then the last thing is when you have ln of what? S to the power n is the same as n ln of x. So you remember all of this from Math 126, right? Math 126. So these are properties of the natural logarithm, right? So with that one in mind, I can simplify this a bit, right? Since this is a quotient, I can write it as, and let me also write this as s minus 2 to the half. This is the same as what? D over dx of ln of the top minus ln of the bottom, right? So because the ln of a quotient is just the difference in the logs, right? So that's s minus 2 to the half. And then I have d over dx of what? Ln of s plus 1. Now for this one, this piece is ln of a base to a power. And then when you have ln of s to a power, you can just bring the power in front to multiply the ln of that base. So that means for this second piece, is the same as what? Let me put everything in square bracket. So I have half ln of s minus 2. Nice. So now the ln is simplified, so that will make my life a little bit easier when I'm getting the derivative, right? So the derivative is what? A difference of functions. Then let's look at this derivative. This one is ln of s to the ln of s plus 1. That one is easier. The inner function is easier to differentiate, right? So what's the derivative of s plus 1? It's just 1, right? The derivative of s is 1, the derivative of 1 is 0. Then divide by the function itself, the inner function. Minus, by the constant multiple rule, ignore the half, do the derivative of what? Ln of s minus 2. So differentiate what is inside, divide by itself. The derivative of x is 1, the derivative of 2 is 0. So you get 1 over what? S minus 2. And then that's your answer. Now, this example is good in a sense that it's going to lead us to something we call logarithmic differentiation. Logarithmic differentiation. Yeah, but please, do you have any questions on this example? Okay. Anybody needs time here? Okay, then let's move on to logarithmic differentiation. So what is logarithmic differentiation? Well, this is one of the most powerful differentiation techniques you ever see, right? In a sense that all the rules that you've learned are okay, right? You can do them. But sometimes, just as you saw for this previous example, you see that sometimes when you're differentiating some stuff, it's much more tedious to do than when it is simplified using the log, right? If I'm just differentiating this, in this case, like s plus 1 over square root of s minus 2, it's much more complicated than when I simplified first before I differentiated. So that's the idea. Sometimes if you're doing a derivative of like a product of some complex function to some power multiplied by something divided by another complicated function, then logarithmic differentiation will probably be the way to go. But in an exam or in a test or something, I'll tell you when to use a logarithm. But when you are working on your own, feel free to use it when you want to. Okay, so now let's look at this example. So example 6, I think it's almost time. Okay, so let me start. Let me end here. Okay. So I'll end here, right? We continue with this on Wednesday. Yeah, so please feel free to reach out if you have any questions, and yeah, and that's all. Yeah, that's all for today. Thank you for your time. Yeah, all the best. You're welcome.